Okay, welcome back, everybody. Yesterday, last lecture, we ended with the following question consideration here, where we thought about all of the graphs that we had shown were non-planar so far. There were only two, and we asked, well, can we compile a list of like all of the non-planar graphs? And right now we have two. The question is, are there more? There are definitely more, right? Because any graph containing K33 and K5 as subgraphs are going to have the same problem, because the corresponding like sub-region of any attempt to make a planar representation is going to run into problems when it gets to making planar representation for that part of the graph, right? So any graph containing these as subgraphs that's not going to be that's not going to work. Um, so that's one thing. So note we already see uh, that any graph containing K33 or K5 as subgraphs will also be non-planar. So and again, anytime the reason for this, of course, is because if you have a graph G that contains either of these as subgraphs, its planar representation would need to, for that part of the graph, it would need to be planar, but it's not going to be able to, right? Because if you had a planar representation for a graph that had these as subgraphs, then contained in that planar representation would be a planar representation subgraph for these, and that can't exist because they're non-planar. Um, so K33 and K5 are non-planar, and I said yesterday that it turns out these are basically the only obstructions to planarity. So these as subgraphs is no good, but let's consider the following. So consider the following. I'm going to draw the following graph. I think this is all of the vertices. Okay. Now I'm going to label a few things. I'm going to label this edge edge A, and this edge edge B. Okay. And so this graph is non-planar. Maybe we'll call this graph G. It's non-planar. But even though it's non-planar, it does not contain K through 3 or K5 as a subgraph. So it is not enough to simply say that the only graphs that are non-planar are the ones that are either K through 3 or K5 or contain one of those as a subgraph. Because here's one that doesn't contain either of those as a subgraph, and yet it's non-planar. So, So then what do I mean by the fact that, K through 3 and K5 are somehow the only obstructions to planarity? Well, there's a reason why this example has been concocted in this way to look specifically like this. So when I was filling this out, you notice this part of the graph probably. And the reason for filling it out this way is so maybe you'll notice, oh, well, what if I replaced the two edges, A and B, with a single edge? Say E. So I'm going to take this graph, I'm going to get rid of that vertex in the middle essentially, and have a single edge here replacing that vertex. So I'm going to get rid of those two edges and replace it with a single edge here. I'm going to label this edge here E. So this edge is edge E now. What do you now notice about this graph? Now that that is a single edge, look at this subgraph. Look at this part of the graph. Everything here and all the edges inside this region. The answer is that now the resulting graph, which is no longer G, we'll say H. H is the graph that you obtain by replacing the two edges A and B with a single edge E. Now the resulting graph H contains K5 as a subgraph. So, what, well, now what do we do? Do we think that the fact that we can do this simple operation to produce a graph that does contain K5 as a subgraph has something to do with the original graph being non-planar? Well, that's what I'm driving at, and it's going to turn out that the answer is yes. So that being a subgraph wasn't enough. That wasn't a fine enough result, but it's like being a potential subgraph if we allow this kind of operation. But this kind of operation is a different operation than we've seen before. This relationship that this new graph H has with G is slightly different than what this has before, because it's not vertex deletion, it's not really edge deletion, it's like edge division, right? Or edge undivision in the case of going from A and B to E. So it's like in going from H to G, you took the edge E and you divided it into two pieces. Okay. So then in a way, you could say that G is like a subdivision of H, because the relationship going from H to G is to take an edge of H and replace it with two edges by placing a vertex in the middle of it. And that is exactly what we're going to call this notion. So quick definition. we start with so let G be a graph. This is going to be a little bit confusing based on that example because the relationship between G and H are going to be flipped. So let G be a graph, a subdivision of an edge E in G is a substitution of a path for E. So this is a substitution of a path for E. So going back to our example here, again, I've swapped H and G. So if we started with a graph that we call H, that here it is, and I took that and instead of the edge E, I have the path A, B, or BA, that would be the original graph I drew here that I called G, right? But this subdivision business is actually doing something more general where I don't have to just like put two edges here instead of one. I could have put 5 edges here as long as it's a path, right? So another subdivision of the edge E would be like E being replaced with this, right? Would work all the same. Now, the graph that I get out of that I might call like G prime, considering this whole thing, would also be a subdivision of H, and this G prime is also non-planar. Also doesn't contain K through 3 or K5 as a subgraph. Yet, H, the thing that is undivided here, relative to G and G prime, does contain K5 as a subgraph. Okay, so in this way we cook up all kinds of examples, and we'll have a full answer to what's going on here in a second. And so we say a graph H is a subdivision of the graph G if H can be obtained from G by a finite sequence of subdivisions. So I'm not going to reuse, I'm going to draw a new example here in a second. So I'm not going to reuse this so that because if I draw any more here, it's going to be incomprehensible. But the idea here is that we don't just have to focus on this happening to a single edge to call this a subdivision. We could have done this to multiple edges at the same time, and it would still be a subdivision. Okay, because this is saying that if we can do this with a finite sequence of subdivisions, then this is the case. So let's do an example here between a graph and subdivision of graph. So here is the graph G. We'll draw it as follows. Let me give myself more room here. Here's the graph G. Let me make the vertices bigger. Okay, here's my graph G. Here would be a subdivision of G. There. Let me make the vertices a little bigger. There we go. So in this case, H is a subdivision of G. Again, this is just to illustrate that this doesn't need to be restricted to a single edge being replaced by a path. In fact, multiple edges could be replaced by paths. So that H may be the result of subdividing G multiple times, multiple different subdivisions. That's the point. Okay. So maybe I should just say, the first result here, which is and going to be an exercise in upcoming homework. Speaking of which, going to have some time here in a little bit where I'm going to have I'm going to field some questions. If you have any, I'll restart the stream when I do this so that it's not part of the lecture recording, so that when you're going back and look at the lecture recording, you don't have like an extra hour of dead time on the video. So here is theorem, which says that a graph G is planar if and only if every subdivision of G is planar. So you can think about one of the directions here is almost obvious. You can think about whether the other direction is obvious and what you'd have to prove to say this. So this proof is going to be in homework 4. But it's like I said, you can imagine, like, if you have, if a graph is planar and has a planar representation, every subdivision is planar. Think about how that would work. Do it even for this example that I've drawn here. See how this affects a planar representation, or whether it affects a planar representation. And then you can think about the other direction. So this is related to what I want to say next. But the question of what the obstruction to planarity was an open problem for a while in graph theory, and then it was solved in 1930 by Kuratowski. So there is following theorem due to Kuratowski in 1930, which says the following, that a graph G is planar if and only if it contains no subdivisions of K through 3 or K5. So this is what I meant when I said that K through 3 and K5 are the only obstructions to a graph being planar. This is it. This is the sole determining thing. This is an if and only if statement. So if a graph contains no subdivisions or if a graph contains no subdivisions of K through 3 or K5, then that's it. That's all that matters. That's all that determines whether or not the graph is planar. So if it doesn't contain any subdivisions of K through 3 or K5, it is planar. And if it does contain them, it is non-planar. So this is a full answer to this. So if a graph is planar, it contains no subgraph that is a subdivision of K through 3 or K5. That's from the previous theorem. So then it's the other direction that requires some attention. So suppose it contains no subdivisions of K through 3 or K5, right? So the forward direction is easy by previous theorem. Backward direction. We're not going to do the whole proof. We're just going to sketch how the proof goes. So to do that, I'm not even going to write the steps. I'm just going to show you the steps that are in the textbook here, because this lays out how this proof goes. So this was not Kuratowski's original proof, I think. This in the 50s, Dirac and Schuster used the following proof to simplify the arguments here. So this is not the original proof that due to Kuratowski. But anyway, the first thing, prove that G is planar if and only if each block of G is planar. What is a block of a graph? A block of G is a maximal connected subgraph of G that has no cut vertex. So that's what a block of a graph is. Second, explain why it suffices to show that a block is planar if and only if it contains no subdivision of K through 3 or K5. Assume that G is a block itself that is connected with no cut vertex. Okay, so once you get to this, once you say it suffices to show that a block is planar, assume that G is a block itself, and we're going to show that it's planar and be done. Okay, suppose that G is a non-planar block that contains no subdivision of K through 3 or K5, so we're doing this by contradiction, so we're assuming that this block is non-planar. We're trying to look for a contradiction here. Then we prove that the minimum degree of G is greater than or equal to 3. We show that this establishes the existence of an edge E, say it has end vertices U and V, such that the graph G minus E is also a block. Then explain why G minus E is a planar graph containing a cycle C that includes both U and V, and choose C to have a maximum number of interior regions. Establish several structural facts about the subgraphs inside and outside the cycle C. It's a little open-ended. And then use these structural facts to demonstrate the existence of subdivisions of K through 3 or K5, which we know can't exist. And that's the contradiction. Okay, that's the sketch of the proof. This proof was written in 1954, I believe, by Dirac and Schuster. So you can look that up. If you want to see the complete proof, you can try to fill in the blanks yourself. Some of the exercises in that section are actually pretty interesting because they have you proving part of this. They have you proving like the first step in that sketch. Okay, so let us now move on to something a little bit different, which is the notion of colorings on a graph. You may have heard this before or come across this even before I knew explicitly of graph theory as a subject. I encountered the four-color theorem, which is it's probably the most famous result in all of graph theory because it's something that even mathematicians outside graph theorists have heard about likely. It's certainly the first place I heard of graph theory. Which we'll get to. We'll talk about the four-color theorem. But the four-color theorem has to do with colorings on a graph. So what is the idea of colorings on a graph? So a quick, I'm not going to write this out, but I'll say an example. We'll say Senate committees or Senate subcommittees. So what about a Senate? Oh, there's another T there. It's all right. This isn't a spelling class. So Senate committees, the example being the following. Suppose that senators in a particular state sit on various Senate committees. And the committees need to schedule times for meetings. Since each senator must be present at each of his or her committee meetings, the meeting times need to be scheduled carefully. One could assign a unique meeting time to each of the committees, but this plan may not be feasible, especially if the number of committees is large, right? You may not be able to schedule unique meeting times for each of them. What could complicate them, of course, is that if multiple senators sit on multiple different committees, so this is always the thing that is going to complicate any kind of meeting things, right? Or even trying to schedule like 5 people for your PhD thesis defense is that requires a lot of effort. It might take weeks to get 5 people to agree on a time some afternoon of the week. So you can imagine doing this for a large number of people, large number of meetings, large number of thesis defenses. We ask ourselves, given a particular committee structure, what is the fewest number of meeting times that are required? We can answer this question by studying graph coloring. So yeah, if I have the question in this Senate example of given a particular committee structure, so some number of committees, some number of committee members on each committee, and we know who is on what committee, and how many committees each senator is on, blah, blah, blah. If we know all that stuff, what's the fewest number of meeting times required? Right, to be as efficient as possible. This is answered by considering coloring. So what is a coloring? Given a graph G and a positive integer, say K, a K coloring of G is a function, you could call it big K if you want, from the vertex set of G to the set of positive integers 1, 2, and so on up to K. If we think of these as K colors, so these are K distinct colors, so if K is 5, these would be 5 distinct colors, distinct meaning I can tell them apart, right? Apologies to colorblind folks that might have issues distinguishing between 2 colors that are very, very similar, but like I said, this is most games now have colorblind modes that add some markers other than just the coloring, so we can consider those new types of colors. So this doesn't matter, colorblind or not, we can still do this in however many colors we want. So if we think of these as K colors, then this function K is an assignment to each vertex of a color. It's a function, so exactly one color. It's unambiguous, right? So to each vertex of one color. So it's assignment to each vertex of one color. Or it's a little awkwardly worded. Maybe I should have said K is an assignment of one color to each vertex. Yeah, let's do that. Here, let's fix the English here. It's an assignment of one color to each vertex. So that, one vertex is not being assigned multiple colors. It's just one color for each vertex. Okay. We say that K, referring to the function that does the coloring, right? We say that K is a proper K coloring of G if for every pair U and V of adjacent vertices, the coloring on U is not equal to the coloring of V. That is, adjacent vertices are colored differently. Okay. You might say, hey, this is aesthetically pleasing, right? If I'm making some kind of like presentation or whatever, having distinct vertices have distinct colors when they're not next to each other. When they are next to each other, they have distinct colors. When they're not next to each other, maybe they don't. This might be how you choose a color scheme when you're making some kind of graphical representation anyway. But this is what we call a proper K-coloring. Now, one more definition is very important. If a proper K-coloring exists for a graph G, we say that the graph G is K-colorable. So K-colorable for a graph does not mean simply that there exists a K-coloring, because that's trivial, there existing a K-coloring. It's that there exists a proper K-coloring. So we say G is K-colorable if there exists a proper K-coloring of G. So if there exists this coloring function K that colors G in such a way that no adjacent vertices have the same color. Okay. So, quick example here. I should have just said let G be C5. C5, the cycle on 5 vertices. So, I'm going to construct a proper 3 coloring here. You can think of me using like red, green, and blue, right? So if I think of 1, 2, and 3 as being, we'll say red, green, blue, RGB. Okay, then let's see here. So if maybe what I could do is if I'm being really, let's label them like this, going clockwise. So I could say let K of A be the color, say 1. Let K of B, I don't want it to be 1 because it's adjacent to A, so that's 2. We'll say, so green. K of C is not adjacent to A. It is adjacent to B, so it can't be 2. So I'm going to actually let it also be 1. That's fine. Now, D is not adjacent to A, but it's adjacent to C, which has the color 1. So I'll have it have the color 2 as well, since it's not adjacent to B. So now I get to E. E is adjacent to A, and it's adjacent to D. A has color 1. D has color 2. So E has to have color 3. It can't have any other color and be a proper 3 coloring in this case. So this K is a proper 3 coloring of our cycle on 5 vertices. Question. So first of all, this means that C5 is K colorable, or sorry, 3 colorable. Question, is C5 2 colorable? So is it possible to use just 2 colors to come up with a proper 2 coloring? And the answer is no. The reason for that is, well, exactly this thing that happened to us when we got to vertex E, right? So at vertex E, you see that if you followed this pattern or this strategy for coloring, you had to pick that 3rd color. Now, the question is, is the way we colored like the best way? Is there some other way of coloring this that you could have just used two colors? Think about that. The answer is still no, but think about why the answer is no. Okay, and so uh, the another way, so an alternative way of thinking of a proper coloring. So now think of a K coloring as an assignment of vertices to sets called color classes. So think of a proper K coloring as an assignment of vertices to color classes. These are sets of vertices with the same color. So the color classes would be, you know, red, green, and blue, or the color 1, color 2, color 3. So I'm putting these into color classes so I could think of saying, well, for this example, in the color class of 1, I have so we'll say color 1, that is red in this case. I have a set containing vertices A and C are color 1. Color 2 contains the vertices B and D. And color 3 contains the vertex E. Okay. So for a proper coloring, this assignment should work in what way? It should work in a way such that the sets you get in this assignment are sets that contain vertices that are pairwise non-adjacent. But we had a definition for that. We had a word for that. These are independent sets. So a proper K coloring assigns vertices to color classes, all of which are independent sets, which means they only contain pairwise non-adjacent vertices. Okay. So this is just yet another way of characterizing these things that sometimes can be more convenient depending on how you have this info laid out. Okay. So the main question that motivates a lot of further questions in this direction. So big question. So a big question. Well, we ask how many colors are necessary to color a particular graph? How many colors are necessary for G to be K colorable? So one thing to think about is in our example on the last page, we showed that the cycle on 5 vertices is 3 colorable. This very easily shows that it's 4 colorable or 5 colorable, because if you can do this with 3 colors, right? If you can color it in such a way that adjacent vertices never have the same color, then of course adding more colors just makes it easier to do that. Right? So if it's 3 colorable, then it's absolutely 4 colorable, 5 colorable, 6 colorable, and so on. It just gets easier and easier and easier to do this. In fact, if you have 5 colors, you can just assign each vertex a single color, right? A single distinct color, and that works very easily, right? So it's clear if it's 3 colorable, then it's all the higher K's. It's all higher K colorable, right? And we saw that 2 colorable wasn't possible. Okay, so 2 colorable is not possible. So 3 is the smallest number here. Such that C sub 5 is colorable or K colorable. 3 is the smallest such K. Okay, so 3 colors in that sense is necessary, and 3 is the smallest. Okay, needed because, well, 2 is impossible, so 3 is the only next option. So this leads us to the following, which is given a graph G, the chromatic number so the chromatic number of G, which we denote as the Greek letter chi of G. So this is why I told you I'm not going to use the usual notation for Euler characteristic, even though I wrote it. Usually this denotes Euler characteristic of a thing, but in graph theory for us, this is what we use to denote the chromatic number of a graph. This is the smallest integer k such that G is k colorable. Okay. So, note, in our example, we have just shown that the chromatic number of the cycle on 5 vertices is 3. Here are some facts or further examples you can verify yourself. So what is the chromatic number of any cycle on n vertices? Well, this is 2 if n is even, and 3 if n is odd. Why is this? Well, consider our example here. Look at this pattern that I used to color. I started at a vertex, doesn't matter, and I started at A, right? I started at some vertex and I assigned it just the first color. Going to the next vertex, I have to assign it a different color. There we go. Now, going back to the next vertex, I could alternate like this, right? I could just keep alternating, and I'm good. The problem is when I get to a vertex that now is adjacent to 2 vertices of different colors. So I have to use the third color in that case. But if the number of vertices is even, a vertex like this E doesn't exist. Because by the time I get to D, I'm closing up, basically. I'm back to D is adjacent to A. Right, my cycle on 4 vertices, this is the last edge. So I could just do this coloring, right? Just the alternating coloring if your cycle has an even number of vertices, and that's going to work. But if it has an odd number of vertices, then you're going to get to the last vertex where this alternating business doesn't work, and you're going to have to assign it the last color. That's not the only coloring you could do, of course, but this is one that works. And so this shows the necessity of that third color when you get to the very last vertex here. And that's only going to be a problem if you have odd number of vertices. So that's the reason for this. What about the paths? What is the chromatic number of a path? Well, it is actually always 2 if you have at least 2 vertices, but it's 1 if you have 1 vertex. But the path on 1 vertex isn't super interesting. What is the chromatic number of a complete graph on n vertices? Well, unfortunately, this is like the other extreme, right? It's just n. You need all the colors possible, right? You need a different color for each vertex because every vertex is adjacent to every other vertex. So using less colors than that's never going to work. So n is the number. This is like one complete extreme, right? What is the chromatic number of an empty graph on n vertices? Well, on an empty graph, none of the vertices are adjacent, so 1. You can just use a single color to color everything, and since none of them are adjacent, that's not a problem. What about the chromatic number? Nope, 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 not. That doesn't exist. The chromatic number of the complete graph, or sorry, complete bipartite graph, partite sets n and m. This is 2. I wonder how you're going to assign the colors there in this bipartite graph, right? So yeah, you only need 2 colors in this case. Okay. So this is like the basics, defining the chromatic number. Now it's natural to ask, is there a way to estimate the chromatic number? Right, so here's some simple examples how we can see how the chromatic number works, but you might guess that chromatic number for a generic graph might be, might be a lot harder to get your hands on. So, question is, can we discuss bounds on the chromatic number? So, for a completely general graph, trying to figure out its chromatic number, figuring out its chromatic number period is hard. That's a difficult problem. So even just if you have a large graph, the number of possibilities just make computing this a hard thing. So we want to think about one fact inspired by what we noticed about the complete graph on n vertices, is that for a graph G of order n, the chromatic number of G is less than or equal to n. Now that's not a super great bound because, of course, this is literally you're using a different color for every vertex. Okay. But this is required, of course, because of complete graphs. All right, so complete graphs necessitate this sort of thing. So complete graphs, it turns out, are the only graphs for which this is sharp. So we know that for complete graphs, chromatic number of a complete graph is equal to n. It turns out these are the only graphs for which this bound is sharp. So if the chromatic number is equal to the order of your graph. That graph has to be a complete graph. Okay, that will be an exercise. So this will be, again, homework 4. You'll show this. So I'll leave that for now. The question, is there is there a straightforward way of coloring? So straightforward. One way to do this is what's the so-called greedy algorithm. So what does the greedy algorithm do? So let's say we have G. It has n vertices, so it has order n. How do I color these vertices? So label vertices, say v1, v2, and so on up to n. Order the available colors in some way. Uh, okay. We can denote these by positive integers. We know n is like the most that we would need here, right? So we start coloring by assigning color 1 to vertex 1, right? If v1 and v2 are adjacent, assign color 2 to vertex 2. Otherwise, we use color 1 again. So assign color 1 to vertex 1. If v1 and v2 are adjacent, assign 2 to vertex 2. Otherwise, use color 1 again. Hey, this sounds familiar. This sounds similar to something we did, right? So, in general, right, color v sub I, we use, so using the first available color that has not been used for any of the v sub i's previously colored neighbors. So this will work. This is, in fact, what we did in coloring the cycle on 5 vertices. And this will get the job done. At the end of this, counting what we are doing here is going to tell us exactly how many colors we need here. Okay, so this greedy algorithm works in that it always gives illegal coloring, but can we, in our example, it gave us the least amount of colors, but can we expect it to always yield the least amount of colors? And the answer to this, of course, is no. There could be, and likely usually is, a coloring not done in this way that uses fewer colors. So this always works to produce a coloring, but may not use the fewest colors possible. Okay. So, what what do we what can we say here? Well, regardless, this gives us another way of bounding the number of colors needed. So, following theorem, for any graph G, the chromatic number of G is less than or equal to the maximum degree of G plus 1. And proof, running the greedy algorithm, produces a coloring using degree of maximum degree of G plus 1 colors. This is because, of course, every vertex in the graph is adjacent to at most the maximum degree of G other vertices, so the largest color label used is at most the maximum degree plus 1. So that's it. Okay, so this is useful as another bound. Right? So the question is, when do we get sharpness here? The question, when is chromatic number of G equal to the maximum degree of G plus 1? Well, we saw ourselves an example of when using the greedy algorithm actually produced the fewest colors used. So in the example we did of the cycle on 5 vertices, it naturally produced the fewest possible colors, so the chromatic number is actually equal to this maximum degree of G plus 1. What here is, this of course wasn't the case for a cycle of C sub 4. So C sub 4, the maximum degree of the cycle on 4 vertices is still 2, but we were able to 2 color it, right? So we know that this is the case for cycles on odd vertices. Question is, are there any other examples? The answer is no. So so this exactly works, or exactly is true, rather, when we are dealing with a cycle on an odd number of vertices. Okay. So this is a result of the following. So this is a case of what's called Brooks's theorem. So which says that if G is a connected graph that is neither an odd cycle nor a complete graph, I didn't write graph here, but you know what it is. G is a connected graph that is neither an odd cycle nor a complete graph, then chromatic number of G is actually less than or equal to the maximum degree of G. The proof of this is a few pages long, so I'm not going to cover it. It's from pages 90 to 92. So you can have a look at the proof if you like. But this proof was not Brooks's original proof. This is like a slight modification, makes it a little simpler. Now, before I talk about the next bound, I have to introduce something else called the clique number. So, quick definition. The clique number of a graph, which we denote with omega G, is defined as the order of the largest complete graph that is a subgraph of G. Okay. So, for instance, very quickly, let's look at these two examples. So, the largest complete graph that is a subgraph of G1 is 3. Can you find it? It's here. It's that triangle there is K3. The largest complete graph that is a subgraph of G2 is 4. Can you find it? Well, it's this block, right? It's this block with these edges. So there's K4 sitting inside G2. So the clique number of G1 is 3. The clique number of G2 is 4. Okay, you might consider why it's called a clique. Okay, or why we reference clique here. So there is a quick theorem involving the clique number theorem, which says the following, and you can think about why this is the case. So for any graph G, the chromatic number must be greater than or equal to the clique number. The proof here, think. Give yourself like a one-line description of why that's the case. Think about what it means, right? So for instance, let's say a graph has clique number 3. So it contains K3 as a subgraph. That's the largest complete graph contains a subgraph. Think about what that means for any perspective, proper coloring of that graph. Okay. Now the question is, can we make this theorem stronger in the sense that maybe we can prove that the chromatic number is equal to the clique number in some way, or is almost the clique number. So question, is the chromatic number of a graph equal to the clique number of a graph? The answer is no. The example to see that, I don't want to draw it. Let's look at the following graph. The question is the chromatic number equal to the clique number? The answer is no, because the clique number for this graph is 5, but the chromatic number is 6. Okay. So for that example, The click number is 5, but the chromatic number is 6. My G looked like a 6 there. Okay. So, what is true, though? We have one more bound that maybe shows different relationship. Recall alpha of G is the independence number of G. So this is the size of the largest independent set of G. Independent set, of course, being a set of vertices that are pairwise not adjacent. So for any graph G of order n divided by the independence number of the graph is less than or equal to the chromatic number of the graph, which is less than or equal to n plus 1 minus the independence number of the graph. This proof is an exercise. I probably won't have this as your homework 4, which will be assigned later today. Might be an exam question. Your midterm will be assigned this Friday, so think that might be a good place for it. Maybe we'll see. Okay. All right. And so we arrive at the next statement. This was something noticed in like the 1800s. I believe it was originally noticed by a student of De Morgan. We arrive at what we will call the 4-color problem. So is it true that the countries on any given map can be colored with 4 or fewer colors in such a way that adjacent countries are colored differently? It was noticed by a student of De Morgan. What's his name? Let's see if it's mentioned here. Francis Guthrie. So maybe we give credit for this problem originally to Francis Guthrie, who noticed in 1852 that it seemed like for every map that he looked at, that for every map he looked at, this seemed to be the case. That you could use 4 or fewer colors to color the map in such a way that adjacent countries, counties, or whatever, you called the regions that were subdivided in this way, were colored in a way that adjacent ones are colored differently. Okay. Um, so maybe I should ask first of all, like, why are we even considering this problem? I've maybe done a bad job of hiding the surprise here, since we just talked about colorings. You might imagine that because of that, this is, well, maybe not so shocking that graph theory has something to do with this. But the progress of the problem, it wasn't immediately seen that this was the case. But basically, De Morgan, I believe, like forwarded this problem, talked about it with Hamilton. Another name in graph theory that we've seen. Hamilton didn't seem too interested in it. Um, but afterward, De Morgan talked to a bunch of other mathematicians about this particular problem, and other people kind of took up the mantle of trying to prove it. Um, Alfred Kempe thought that he had a proof in 1879, but it was found about 11 years later there was an error in the proof. And so it turns out that this problem is extremely hard to prove, even though it is very easy to state. And this remained conjecture all the way up until, like, I think 1979 or 76, sorry. So the question is, how can I turn this into a graph theory question about coloring? Well, first of all, um, so first we replace countries with vertices and their borders with adjacency relationships. So here's two easier examples. So if this is like some map of some region, right? So this might be what it looks like, or some subdivision of a county or something. We could talk about this in terms of, okay, there's this region, this state or country that corresponds to this vertex. It is adjacent to this one, this one, this one, and this one. So it has degree 4. Here it is, degree 4. Here are the ones it's adjacent to. And we keep track of all of these in a similar way. Maybe we label them, right? 1, 2, 3, 4, 5, 6, 7, 8, whatever, and we put the labels here so that it's easier to keep track of. Here, we have map of the southeast, U.S. Tennessee borders. Tennessee and Missouri, I think, have the most number of borders of any state. They both have 7. They're adjacent to 7 other states. Here, we're only looking at the southeast. So in this particular submap, right, Tennessee is adjacent to North Carolina, Georgia, and Alabama. So here's Tennessee, here's North Carolina, here's Georgia, here's Alabama, here's South Carolina that is adjacent to both North Carolina and Georgia. Here's Florida that is adjacent to Georgia and Alabama. So in this way, we replace the countries with vertices, and now it becomes clear that a coloring, right, of the vertices is a coloring of the map. And so we have reformulated this problem, this 4-color problem, into the following fact here, which is now called the 4-color theorem. And the 4-color theorem says every planar graph is 4-colorable. Well, that's quite a bound on chromatic number, right? This says that every planar graph is four colorable. Okay. So, the proof of this did not come, despite lots of effort, did not come until 1976. This is due to Kenneth Appel and Wolfgang Haken. And it is the first computer-aided proof. What should I say here if I want to be precise? First computer-aided. Maybe we should say it was the first like accepted computer-aided proof. Because like obviously you could have like some of the early computation engine stuff running through various algorithms. Like I'm not. I'd have to actually go back and look at to make this 100% precise, but this is most certainly the biggest result in mathematics. It's the first example of a large, like major theorem being proven with partial computer aid in the sense that computer used to check or to verify many, many thousands of subcases. So part of this was brute force in the sense that the problem was reduced to thousands of cases, which had to be checked by computer, couldn't be checked by hand. So this naturally was extremely uncomfortable to a lot of people for good reason. Because the standard of mathematical proof is very, very high. So this eventually was accepted. There's a lot that you could say about this. You could look into the specifics of this. It's all very interesting. This is the thing that I think even up until now there is not a simpler proof of this. So there is not a proof that does not rely on this sort of thing. I think I would need to look into that. I'll find out by tomorrow if this has changed, but I don't think it's changed. I think this is still the case that this sort of argumentation is required. So unfortunately, this is just something that had to be done. So there, even upping it to 5 colors is substantially easier, to the point that we can actually prove it in the 5-color case, although I'm not going to go through that proof. I'm just going to state it. So here is another example. We could call it the 5-color theorem. Every planar graph is 5-colorable. The proof, unlike the 4-color theorem, which relies on a computer to prove, this proof is entirely contained on the pages 95 to 97 of the textbook. So if you're interested in how this can be done, you can have a look at that theorem. Just upping the colors by 1 makes it substantially easier. This is essentially the same proof that was completed in 1890 before, back when they were still making, back when like some of the first original attempts to prove the 4-color theorem were being made. This was proven way back then. This is substantially easier. Going down to 4 colors, this is true. This is a very amazing fact. But yeah, just reducing your number of colors by 1 introduces extreme complication to this problem. Okay, this is how there are many, many things in maths and completely disparate and disjoint areas of math where this is the case. It's like doing that one further step really makes a difference in turning a problem into a real nightmare. So anyway, that is that. Let's see how much time. I think I'm essentially out of time. So I think this is. I think I'm like 1 minute over. Actually, no, I'm only like 30 seconds over. Great. So this is a perfect place to stop. We will talk about chromatic polynomials here tomorrow. I'm going to stop the stream now, and I'm going to restart the stream here in like 10 minutes and take any questions you might have about homework. Again, as I mentioned, I won't be as helpful as I could be in order to kind of nudge you in certain directions rather than just give you an answer, but that's how it's going to be. So anyway, if you have questions about the homework that is due tonight, stick around. Like I said, I will post stream link here in we'll say like 10-15 minutes, and I'll be there for like an hour ish. So anyway, that's the plan. So I will see you all here shortly, either tomorrow or in like 10-15 minutes.